Mm. So this just a small presentation to capture overview, the basic overview of design. So in designing a water reticulation system, there are some basic steps or there are some basic requirements that you need. And this again and again, and it captures design a water reticulation system. Now, if you are asked to design a water reticulation system from the point of a consultant, what and what do you need, and what are required of you? The first thing you need is you need a map, you need a topography. Then number two, under the introduction, you need the description of the area. So the first step in designing a water reticulation system is you need a map with a topo. So what is topo? Topo is basically showing the level, showing the spot height, showing the elevation. Because why do you need that? You need it because pressure is a function of elevation. And 95% of water reticulation system is via gravity. So you need a map that shows you the elevation of the place, that shows you the difference in height and everything. So that's the first thing you need for you to start your design. Then number two, you need to have a description of the area. Where is it located? In describing the area, is it surface water? Is it groundwater? Is it spring? What kind of water source do you need? What are the reliability of the water source? How sustainable is the water source? What is the tendency of the water source being contaminated? Is it an agricultural area? Is it a mining area? What is the aquifer formation? Is it a good aquifer? What is the hydraulic conductivity? You start doing geotechnical tests. You start to talk about the history of the place so that you know your water source, how to protect it, how to extract it, and how to make the whole design sustainable. So you need those two things, not just the map and the topography, but you need a history, a background of that area. When you have established those two parameters as an introduction, you now go to description of calculation basis. In other words, you start to do three things. Number one, what are the water demands of different users? Low density areas, high density areas, medium density areas, they required different water demands. In Abuja in 1978, 100 liters per capita per day was used to design Abuja. In Germany now, in southern Germany, they're using about 120. In the north, they're beginning to come down to about, because it's becoming more difficult for them. Most times surface water needs to be treated, and it's very expensive. In the south, they have access to some natural lakes that they can get water from. So it's easier in the south. In some rural areas, the water demand is sometimes 80, 60. From the Federal Ministry of Water Resources, I know that rural areas can go as low as 50 liters per capita per day. All of us are are engineers, so we know what 50 liters is. Number two thing in doing water design is you ask about the expected growth. We do what infrastructure design based on expected lifespan. If I want to design the water reticulation for a place like, say, Gwagwalada, I will need to ask myself, for how long, for how many years am I projected? 25 years, 30 years, 50 years. It is the value of that 50 years I will use. Let me repeat it again. If I'm designing for a new virgin city or a new layout, my design must be able to capture or accommodate the lifespan of that water project. If I expect a water project to last for 20 years, it means I need to extrapolate the population to accommodate 20 years. So if the population today is 10,000 people, and it's going to be 15,000 people in 20 years, it means I'm going to use 15,000 to do my design. That's what we're saying. I'm going to use 15,000 to do my design to get my water demand, and by extension, it will influence my pipe sizing. Then number three, still under the calculation, how you form your calculation basis or takeoff, is you need to ask yourself, are there going to be future developments? Maybe today we are expecting that in 20, 30 years time, there will be a university. So it means I must capture that population explosion in my design, even though we're not yet there, but I have to capture it. Very, very important. Then, after you have done these 5 things, or in 2 subgroups, you now go over to the next one. Okay, somebody said the materials are not downloading on my PC. Just be patient. It will download, please. Maybe it's your network. Network is bad this morning. All right. Okay, now, the next thing you do now is that you now present these figures that you have gotten, which is the water demand. And the next thing, you now draw your distribution network. You draw your distribution network. When you have drawn your distribution network, you now analyze them. We're all going to do all these things. You analyze them to see that there are no pressure, to see that the flow is okay, the velocity of flow is okay, the pipe sizing is okay, there are no negative pressure anywhere, that the minimum design pressure of the system is met, the minimum flow velocity of the network is met, the minimum water demand of the users is met. That is what the analysis entails. So let me take you through again. The first thing, you must ask for a map, which you could get either online through Google Map, or through the architect, or through the infrastructure surveyor. And those maps must have topo values, contour lines, spot heights, everything is all about the topography of the land. The idea is that when you come to your water design, you must establish 2 things. Number one, where is the highest point in the catchment, and where is the lowest point? The highest point is expected to be where your elevated tank is going to be. Either it's an elevated tank, it's a ground tank, or it's an underground tank, or tank is tank, or reservoir. Let's use a more technical word, your reservoir. So your reservoir is expected to be located in the highest point. So that's why you need the topography. After that, the lowest point should also be taken into consideration, because you must make sure that the pressure in the system is no more than 8 bars. I will still come to that. You cannot allow too much high pressure. You must not allow too much low pressure. There's always a range. There's always a range. We'll still come to that. So it is about 2 boundary conditions. Highest boundary condition and minimum boundary condition. In standard design, we expect you to have at least 2 bars. Minimum average of 2 bars, not more than 8. I'm aware in the last 5 years, there have been a lot of improvement in pipe materials. There have been a lot of innovations that can tolerate 12 bars, 15 bars. But safety demands that you limit your pressure to 8 and optimally 2. It does not mean if you have 1 bar is bad, or even have 0.5 bar is bad. No. But at least there's always this thing about acceptable limits, okay, for a normal design. There could be extremes. There could be, challenges. But this is what you should aim for. Then after that, you must know about water demand for different users. Like in a residential area, water demand is between 100 and 120 in a standard universal design. But here in Nigeria, rural areas, Federal Ministry of Water Resources sometimes uses 60, 50. In fact, I've had one, they say 30. I told them it's too poor. How can you say a human being to use only 30 liters? But then, when you factor in that these rural areas, some of them don't use flush latrines. Some of them don't use showers. Some of them don't even bathe 3 times a day. Some of them don't even have cars to wash cars. They don't have gardens. So you discover that their water demand might not be, they don't have washing machines. So their water demand might not be as high as those in the city. So that is why you must factor it in. A hospital, a patient in a hospital requires minimum of 200 liters of water per day. Now, these things I'm mentioning are all in the material I asked us to read. So when we, after this training, we will still have time and go through them. These things are already in the PowerPoint that I've sent on the cloud. Like I said, I'm not going to repeat them so much because we don't have that luxury of time. Okay, after that, you now go to desk work. You now start your design by presenting all the figures you have gathered. And what are those figures you need in a water reticulation design? If you want to design a water facility, I want to share something. Okay. So let me share my whiteboard. Okay. So basically, gentlemen, in a water reticulation design, there are 4 basic parameters, and they are broken into 2. The first one is called the pipe parameters. You need to establish the pipe parameters. And what are those pipe parameters? The pipe parameters are 1. What are the lengths? Length of pipe or length of section, length of each section. So assuming I'm coming from Aminu Kano to Ademola de Tokumbo, that the 2 junction. So from junction 1 to junction B, what is the length of the pipe? I need that length. I need that length because that length I need to calculate my losses, my velocity, and many other parameters. Then the second parameter you need, pipe parameter, is what is the diameter? Remember, I said there are 4 of them. So you must ask yourself, what is the diameter of the pipe? Because the diameter of the pipe is key. The diameter of the pipe is key. If the pipe is undersized, water will not flow. I have seen consultants that design water reticulation system and they spend millions. And wrong pipe, water will not flow. Why? Because the pipe is so small. And as a rule of thumb, from my experience as a consultant, not just as a trainer, if you are designing any estate layout or any city layout, please, your minimum pipe design should be 75 mm, 2 inches pipe. I've seen people using 2 inches pipe. It is absolutely wrong. Quote me anywhere. The minimum, and those minimums should be at the tail end. At the upstream, you can have as high as 6 inches, 150 mm. Then as it's going down, it's reducing. Can reduce to 4, can reduce to 3. But I can tell you, the one that gets into the houses or anywhere, field, market, shopping or whatever, should be at least 2 inches pipe. So in doing water reticulation, you need to establish 4 parameters subdivided into two subgroups. I call one pipe parameters. What are the pipe parameters? The length of the pipe. What is the distance? Am I doing this water? And then what is the appropriate pipe size I need? The second one is called elevation parameter. And under elevation parameters, you must talk about what is the water demand at every node. Okay. What is the water demand? Okay, sorry, I call this one is not elevation parameter. This one is called node parameters. And under node parameters, you must discuss what is the elevation at that point. What is the elevation at that point? The second one is what is the water demand? Some people will call it water demand, some people will call it flow. Okay, so I think one of us has this. I'm not called. Okay, so one is called elevation parameter. Why do you need the elevation parameter? That's why surveyor goes to site. You need the elevation at every point because the pressure at every point is the difference in the elevation. The pressure at any point in your node, in your water network, is the difference between the reservoir and the tap point or the fetching point at that point, or just call it the elevation of the house. So that will give you the pressure. And with that, you know whether water is flowing from point A to point B or from point B to point C. You get the point? Are we together? You need, that's why when surveyor goes to site, what does surveyor go? Surveyor goes to do two things.
Yeah, together.
Okay. Surveyor goes to do two things. The first thing surveyor goes to do is to measure the elevation, to know the height, to know how the undulation of the land. And with the undulation of the land, you can now determine the length of each section. What is the distance between Airport Road and Gwagwalada? That length is what you need to calculate your losses, to calculate your to calculate your losses using the frictional factor of the pipe material. Okay, so two things surveyor does for you, but it looks like one thing. He does elevation, take the spot height, he uses GPS and get the height. When he now goes to his office, he plots it. And you, being a AutoCAD expert, being an engineer, you can now measure a point A to point B, you measure it out and you get out the sections. With the length and the sections, you can establish two parameters, leaving you with two more parameters. The two next parameters is what you, the engineer, will determine. So in other words, we need 4 parameters in total. 2 can be gotten once the surveyor goes to site. But the remaining 2 is the diameter of what diameter of pipe do I need? But for you to get the diameter of the pipe, there is a prior question you must answer. What is the flow? What is the water demand? Some people call it water demand, some people call it flow, some people call it discharge. Whatever you call it is the same word, it's the same thing. You can use them interchangeably, depending on what you are treating. Whether you call it discharge, you call it flow, or you call it water demand, it's the same thing. Once you get the flow, once you get, which is also the same thing as the discharge or the water demand, you now use it to calculate the pipe size. When you now calculate the pipe size, your 4 parameters are done. With your 4 parameters, you go back to the layout and detail your design. Gentlemen, that is all you are here to learn. This is all you are here to learn. How to determine these 4 parameters. 2 of them will come out once the surveyor goes to, once you go to survey the place. The other 2 is what you, the engineer, must determine. And once you determine it, you now go back to your layout and then detail it for the layman, for the site man to execute. We'll still come to that to detail, but many of us have only seen detailed work. You see a pipeline, they will draw the diameter of the pipe using the sign of diameter, theta. They will put the elevation for you there. They will put the slope in terms of percentage. Maybe they say 0.5%. Then they put the elevation of point A, elevation of point B. So we're all coming for that. But I want us to know that this is the 4 parameters you need. In the past, once you have gotten the water demand, the next thing you do is now use Manning's and all those hard formulas, hard cross, name it, the Euler equation, many Chesney-Manning, the Weisbach equation. What's that one again? Manning's equation. Yeah, that's it. But today, we no longer use those equations. We use charts. Today, we use charts. Everything is charts. You go to charts, you read up your values, and the pipe sizing will just pop up. So that is that. Any questions so far? Okay, so I go back to my this. So when you talk about the first one says map and elevation. So this is a design. I'm using this as a case study. It's a design we did those days when we were in Germany. You know, that's one thing I said I will say in this training. The best way to learn sometimes is to use case studies, to use not just theory. You practicalize, you demonstrate it. So let me quickly do this because I have like 10 minutes to do this. So this is a map. So you need to establish the map. You now establish the history of the place, the history, the background of the place and everything. You now develop your design objective. You must have a design objective. Your design objective should be that you want to provide water, clean, potable water, in the right quantity, in the right size, in the right quantity, and very sustainable. Then after that, you study the area, you describe the study area, you talk all the stories, you explain, you know, sometimes as consultants, just to fill up the books, right? You describe how the place is suitable or how it's not suitable. You describe how the water, you're going to source the water, how each of the water is going to contribute, how you're going to take some from surface water, how you're going to take some from groundwater, why groundwater is possible, why it's not watchable, why you need a treatment plant there, or why you don't need a treatment plant, why one market close by should be relocated so it doesn't contaminate the water source, why farmers should move away, why there should be a buffer around the water area. Like this place in my screen, you can see that this is like a buffer. This is the best place to locate your water area where it's free. Like what is happening in Abuja now? If all of us must know, Lower Usman Dam is being encroached from Pape. It's going to be a disaster in the future if something is not done. Because as people are encroaching, there is open defecation going on. There is human settlement going on. There are people, anthropogenic influences coming close to Lower Usman Dam. So I want you to imagine you have a water source and there's houses around it. I mean, somebody can just go there and poison the water and everybody in the city will die. A terrorist can, an extremist can do that. There's a need for you to locate water source where it is free from contamination, where it is free from danger. So these are the things you explain in your write-up as a consultant. You can draw the AutoCAD section, you draw the map, you draw the picture of the area, you do things, you know what we do as consultants, just to fill up the books and make it, so that your money will be huge enough. Okay, you can draw the place to see the inundation. What does this map tells you? It will tell you where your tanks might probably be located. I remember in Plateau State, a place called Mangu, one of our engineers was telling us, I can't remember what he said, but I know that the distance where they located the highest point to the city center is about 28 kilometers or there about 10 kilometers, I can't remember. Like in Abuja now, our tanks, the major tanks are all located in high areas. I don't know if there's somebody here is in FCDA. If I have somebody from FCDA here, but if you look at it, you know that they are all located in high areas. So, somebody's having an issue. Okay. Somebody give me 1 minute. Okay, let's continue. One of us is having difficulty to join in. So the next thing is you try and draw the section. Sometimes it is not, you must not provide a centralized water supply system. Sometimes centralized water supply system is not possible. And when such is not possible, you go for decentralized. Decentralized. In Abuja, people sometimes, yes, we have a centralized reservoir, a centralized water treatment plant, but we don't have a centralized water distribution structure system. Abuja has about 6 tanks. They are going to be up to 10 tanks, but 6 tanks have been built. So every region, who say zone 1, who say has a tank supplying it water. Maitama has a particular tank supplying it water. Apo has a tank supplying water. Good has a tank supplying it water. Warempa has a tank supplying water. But there is a single pipe from the treatment plant supplying their water. So if you look at that system is a decentralized. They are not all coming from one tank. But the treatment plant is centralized by virtue of location in Lower Usman Dam. So I want you to begin to put on your thinking cap and begin to see the differences. Now, look at my map. You discover that there's no way I can do a water reticulation system on the two elevation within the 2 valleys. How do you pipe it? So definitely what I need to do is to provide a system for left part and a system for the other part. Did you get the point? That is what I should do. Because without that, there's a problem. I cannot pipe from here to here. So, like for instance, in some development, you see people talking about phase 1, phase 2. Yes, that's also another way. I can do phase 1 and phase 2. And phase 1 and phase 2 will be only be joined by supply, but distribution will be independent. I can also do independent supply, independent distribution. Right? So phase 1 will have their own borehole, have their own upper tank, have their own reticulation. Phase 2 will have the same thing. It's possible to have such a structure, depending on the challenges you met on site, like in this case. So that is that. Then the next big thing I want to explain today is that in your layout, you should also look at what we call zoning or pressure zoning. It is not possible to locate, for those who know Abuja, it is not possible for you to locate a water tank in Kokolaga and supply it in Wuse, which is a distance of almost 60 kilometers. No, it's not possible. You must find another method. The distance is too much. Some places in Jos, it is not possible to supply everybody within the community with water. Why? Because some places are so high, other places are so low, that if you want to supply everybody with water, then somebody will be getting water at a very high excess pressure. Yes, somebody will be getting water at a very high excess pressure. So then you now imagine what is the need. Because like we said earlier, there's always a minimum pressure you need. The pressure must not be so massive that it starts to spoil things in the house, for instance. Okay? It doesn't have to be so much massive that, for instance, let me digress a little bit. If you are doing a water reticulation for a place, one of the questions you must ask is, what is the highest elevation of that place? that highest elevation also involve what type of buildings are coming there. Is it bungalows, one-story building, four-story building? If you do a design and you assume it is bungalows, and tomorrow they build four-story building, I want you to know that you have lost almost 2 bars of pressure. How many of us remember those days in our hostels, in our universities, that or in the cities, if you are living at the upper floor, you don't get water sometimes. Those on the ground floor will be getting water. And it is only when those in the ground floor are not fetching water that your tap will start to run. That is a poor design. Either a poor design by the designer or changes in development has fought. And that is why those, when FCDA and development control are very strong in Abuja, they will tell you the type of building to build in every area. So people don't understand why.
Hello.
Yeah, we have lost him.
Yes, because I can't hear him from my end.
Yes. From the mention of FCDA in Abuja, he went off.
Maybe it's network problem.
Okay, we probably would just note where we lost him so that he can pick up from there.
Okay, so I'm sorry, network. I'm back now. Network took me off. I've
Okay,
my phone.
okay.
Yes. So now, so if there's ground, if somebody's on the ground floor and you are designing for a 4-story building, you must, I'll come to there. You must factor the person you use as a reference will be the person at the 4th floor, not the person at the ground floor.
Please share your question again.
Okay. If you are designing for a place that has 4-story building, the reference point is the 4th floor, not the ground floor. If you use the ground floor and do your design, okay, for instance now, you can see that some people who build 2-story building, when they are putting an elevator tank, what do? They go higher. Why? Because the person at the last floor is the reference. That's why in city center in Abuja today, you cannot build something more than 12-story buildings. The reason is that if you must build more than 12-story building, then you must provide your own water. Because one dam cannot supply you water. None of the tanks can take 12-story building. So it means you have to come, have a reservoir, maybe at the ground floor, then build your own elevated tank. So when you take water from the raw water tank, you can use your surface pump and push it up. Then from up, it comes down via gravity. That is why in building approval, they must know what you want to build and then tell you whether it fits in. Not only there, not only based on the water parameters, it could also be based on the electrical parameters, other infrastructure parameters. You don't just come to a place, you say, I want to build, you just come to Abuja and say, I want to build towers. If you build towers, good, fine, but just know you're taking care of yourself. You're not using the centralized water supply system. That's why people in Gwarimpa today, if you're in Abuja, many parts don't have water. Because the tank that's supposed to supply Gwarimpa has not been built by FCDA. So they're using the tank for another place. Therefore, some high elevated places in Gwarimpa can't get water. It is not possible. Water cannot flow from low elevation to high elevation. So in doing your water design, you must look at the layout and check and see if you need to zone them. If you watch my screen, you see I'm having zone 1, zone 2, zone 3. Like for instance, zone 1 here says all the houses between elevation of 310 to 270, I will provide them with tank 1. And that tank 1 will be at this altitude. So the altitude of tank 1 will be at 345 or 350. By the time you supply 350 minus 310, you'll be getting 40 bars. 40 bars is very good. Each floor is about 0.5 bars. Each floor is 0.5 bars. So 40 bars means you can build a 8-story building. So that's enough. And for that 40 bars, using a column of water as 10-meter height, it means the difference of 40 means 4 bars. It means in this zone, I'm sure of, without considering losses, I'm sure of 4 bars. If I put in losses, bend, pipe size, undulation of land, maybe I'll end at 3 bars. So this is good to go. If you come to zone 2.
Hello,
Yeah,
sir. I hope you are still recording, sir.
Yeah, recording is in progress. Give me that signal. I'm sure. Okay. Yeah, I'm sure, sir. I'm sure it's yeah, it's recording. Look at the sign. Okay. It's recording, sir. Okay. So if you look at zone 2, zone 2 can also mean tank 2. Zone 2 means all the houses within elevation of 270 and 230. And I'm going to provide them with tank 4 or tank 2, whatever tank, forget about it. And that tank will be located at elevation of 310. So if you look at 310 and 270, that's giving you a pressure of 40. If you look at 310 to 230, that's giving you an elevation of 70, 80, which is at the limit. I can tolerate it. If you look at zone 3, all the houses that are within elevation of 300 and 255. Not in every design you have this kind of undulating land. This is a unique place. If it's in Abuja, you can just have one zone or 2 zones. But unfortunately, Abuja will have about five zones. We're supposed to have like 10 zones. But so far, FCD have only built like 4. They are building one now in Apo. Tank 6 is being built in Apo to service Apo and Gudu. That's the one I know. But I can tell you from the master plan, we have up to 10 tanks, which is technically meaning 10 zones. 10 zones means how to optimize the pressure because it is via gravity. So you need to kind of catchmentalize the houses based on where they are sitting, based on the high elevation height. So here is zone 3, 300 to 255, and I'll locate the tank at 330. So if you see 330 minus 300, that's about 30. So it's coming down, but you don't have a choice. It has to come down, and so on and so forth. I hope you're all following. So after doing that, you now start to plan the water system. You talk about the background. I talk about the background. You talk about why you are making your decisions and why your decision is important. Then the next thing, you now go to water source. What water source am I using? There are many available water sources. You can use groundwater. You can use spring water. You can use surface water. You can use water from long distance water supply. So it is not all the time that you must drill a borehole. I can decide to use water from Abuja Municipal. All I need to do is maybe I'll build my own reservoir so that when I take from them, I'll put it in my reservoir so that there will always be water available. Okay. So of course, if the price and the cost is good for me, if not, I'll drill my own borehole. So in the water source too, you analyze all the parameters of the water source, if it's cost, how to drill it, you do all the analysis, geotechnical survey and everything. Then the next thing you do is that you distribute this population and town into what is the population now and what is the population in the future. Remember, we are using the future population for calculation. Don't forget that, please. But it is good to know what is here, so you apply the appropriate population growth. For instance, all of us know that if I'm designing a water reticulation system, a place like we say Anyanya, I will put more sizing, more safety factor in Nyanya, because that's where the population is growing. Wuse have already grown, can't grow more than it has grown. Or if I'm doing a water design I'm looking at a rural area, can't find a rural area, it cannot be the same with the one I'm doing for a place that I know that the city is going to grow. Let's say there's a university built in Wawalada today, and I'm asked to do a water reticulation to that area. I know that with time, houses will spring up. So if I'm using a population growth, I can use like say 5%, 10% or higher, when Nigerian average is about 3.5 or 4%. Then if I'm doing for rural areas, when I know there are rural urban migration, I might just do it normal. So you go online, you choose the appropriate population parameters, and you extrapolate your population. The next thing you do is that you do water tests. Whichever water source you have chosen, you go and do a test. You do a test and make sure so that the test will help you know the kind of treatment method to apply, and then to know how to select the best. Of course, all of us know that the best water is the groundwater, but be careful with groundwater. I've seen some areas in the Northeast where their groundwater has become lead poisoning for them. I've seen some areas in Niger Delta where surface water is a no-no because the presence of gas flaring and iron in the water. So you need to do a water test, analyze the water you're using so that you know which one to choose. And even in knowing which one to choose, you know how you need to prepare your budget for water treatment. It's not good that you do a design, provide water, and the water is not drinkable. Or suddenly you don't have money to treat it again. So all these things must be put into place. Then the next thing, okay, I've asked this one. You now distribute the water based on the different areas. So if you look at this one, which we're going to do now, you see that we have industrial north, we have housing Fochley, we have commercial east. So in our own context, I wanted to see this like Wuse Zone 1, Wuse Zone 2, Abaji, Galpi, Maitama, Asokoro. Why is this distribution important? In doing pipe design, we have 3 to 4 layers of pipe. Listen to this. We have 3 to 4 layers of pipe. So we have to. Well, that's not what I need. I need this one. Test. Good. We have about pipes under pipe layers or pipe types. We have like, let me call it the main. Have the main pipe. Some will call it primary pipe, primary distribution. This is the most important. Some of us that live in Abuja, you can see that last year, the Chinese started the second Greater Abuja Water Supply Scheme. You can see them laying pipe along Airport Road, a 1.5 diameter pipe. That is what we call main pipe. Along Kuba Road, from Lower Usman Dam, you see a 1.5 meters diameter pipe. Those are the main. These main are the most important. Because if you get it wrong, the one that follows is already condemned. The second one is called the secondary. Okay, sometimes the main, like in the case of Abuja, can be from 900 mm sometimes to 2 meters diameter. Yes. The one that you see in Abuja now, as long as I know, is 1.2, 1.5 for the main. Then, when from the main, the secondary will tap. The secondary will tap from the main. The secondary can now be 600 to sometimes 300 to 200, maybe 150. These are called, or sometimes 100 too. Depends on the house, the scope, the scale. Okay, if it's a small estate, okay, the main will be like 200 or 150. Yes, the primary pipe will just be 200 and 150. Then as it enters the estate, it starts coming down the street. The secondary will change to 100, 150. Then finally, you now have the tertiary. Can't spell it. Sorry, my can't spell it, but I know. Why shouldn't I? So the last one would be the tertiary, yeah? The tertiary pipe. That one can be, like I said, that one will not be 100 to 75 to 50 sometimes, but I advise you let it be 75. Then the other one will not be, this one is not included, but you can call it building services pipe. That's the one you now start, your plumber will now start using 1 inch, 2 inch, all those ones. Those ones are not part of, are not the infrastructure. They are not. You know, we are talking about infrastructure, not building. So you're not start talking about those ones. But these are the 3 key ones. This one can be called, sometimes this one is also called transmit. Okay, no, transmission is different. Transmission, there's an upper layer one, which is not here. There's a one called transmission. Transmission pipe is the one coming from the treatment plant to the main tank. Transmission pipe. Please don't confuse it with the main pipe. The main pipe is the first pipe leaving the reservoir. But the pipe conveying water from the treatment plant to the reservoir is called transmission. So it's not part of the 3 I want us to understand. The one leaving the tank is the primary. So what primary does that, it leaves the tank, it starts going, it gets to somewhere, it changes to secondary, start going through the streets. Then from the streets, it starts going through the houses. So as it's going, it's reducing because the water demand is decreasing. Any question? Okay, there's a question on the platform. How do we estimate the volume of water and its sustainability from different sources, especially in dry region? How do you estimate the volume of water? Well, I think from my small experience, is a pump testing. You know, we don't do pump testing in Nigeria. When you drill a borehole, you're supposed to do a pump testing of the aquifer to know if the yield is adequate. You pump test. Pump test means you pump the water, you bring a tank, you bring a gen, you bring a hose or a pipe, you reduce the discharge of the water to a certain volume and allow you to run over some hours. Then, if it can last for 24 hours, then it's a good yield. But if it stops somewhere along the way, then you know that your rate of extraction is less than the rate of this recharge. So what you do, you adjust the discharge, what you expect if you are coming to that anyway. Then you do some testing. But we don't do it. I'm sorry, we don't do it here. But that's the way to do it. That's how to do it. The other way to estimate the volume of sustainability is through river gauging. If you are using surface water from a river, you know that during rainy season, there's a lot of water in the river. In a lot of dry season, there's no water. The volume you are going to use is the volume for the dry season. Yes. The volume you get in that river in the dry season. Remember, you don't take 100% anyway. If you are taking 60 or 50 or 70%, because you must left some to continue downstream to preserve biodiversity. Okay, the second question. Okay, that's the only question I have. Okay, any other question?
I don't know if I can ask my question now when we're done with the presentation.
If you can wait,
Okay.
we are done. Let us fire on. Let us fire on. Okay. Now, I'm done with that slide. I want to go to another thing. I'm done with that slide. So you can just go through the slides more. But I wish I can start our calculation here. I don't know that that's required. Let me leave it. I want us to estimate some of these things, but at least we understand what is happening here. But let me use it to explain something. Please get your pen. Get your pen, get a piece of paper. Let's do something. Let's do something. Let me on my whiteboard. Let me clean it. Good. Now, let me discuss water demand. We say that we are engineers. We are engineers. So if I'm asked to design what is the water demand of a three-bedroom house, what is the water demand? What is the water demand? How do I go about it? Number one, you use your code and standard and said, what does the standard said about water demand? How many liters of water per person per day? So let's assume 100. There's a chart in our material, is there. You see it. Depending on whether it's a hospital, a school, or whatever. So for a housing, for a residential housing, is about 100 liters per capita per day. So liters. It's 100 liters per capita per day. Okay. 100 liters. I want you to get these liters. Yeah. Capital C per day. Now, 1,000 liters is equal to 1 cubic meter. Let me put it that way, right? Then 1 day is equal to 60 times 60, which is equal to 3,600 seconds. In designing your pipe, remember our priority here is to calculate the pipe size. Is to get the water demand, and with the water demand, we get the pipe size. So let me first of all, the water demand is known. The water demand is known. We are using 100. Why we use 100 is that in one of the tests I have given us, you see how he broke it down. In a day, you require between 3 to 10 liters of water to drink. You require about 40 liters of water to wash. You require about 20 liters to cook food. You require about blah, blah, blah. It's all there. How you come about 100 or 120, whatever you choose to use. So that one is already established. So the next thing that needs to be established here now is the pipe size or the total water demand. So we will know, let's say that each 3-bedroom, how many people are in each 3-bedroom? Let's assume it's 8 people, or let's be lazy. Let's say 10 persons.
Hello, sir.
Yes.
Sorry, I think this the timing there should be times 24. I think that's this one you wrote is for 1 hour. The 360,
Thank you, sir.
the 3. Yes, sir.
Times. Where's my times again? Can't find it. Okay, times. Thank you. And it will give you 8,600. You remember our hydraulics? Are we together? So 1 hour will now be 60 times 60, which is equals 3,600. Thank you. Now, why am I going to seconds? In doing modeling, generally in general universal modeling, you do model based on the tiniest parameter. You discretize, we say discretization. In water reticulation, I'm interested in not what flows every day or every hour, but what flows every second. Seconds, because you need water. So you need every second must be in your house every second. So we're going to design water. If you design water based on hour or day, you're going to get the peak size. The one you design by day is the one bringing water to your reservoir. You design it by hour. You don't design it by day because sometimes you pump 2 times in it. You pump every 12 hours. Sometimes you pump every 8 hours. So you do that design based on hourly demand. I'm coming there. Hourly demand. But in designing the water that comes to your house, you do based on seconds demand. So we're going to determine we need 100 liters of water per person, per capita, per day. But what do I need per seconds? So what you need per seconds is you do this conversion. So this 100 now, liters, you leave it in liters. Then per day means per capita means 1, let's say for 1 person. Then this day now becomes 8,600. So here we have 100 divide 8,600. It will give me 0.0012, let's call it 12 liters per seconds. This is the parameter I need to design my pipe. So now, back to the question, 3-bedroom house, what is the water demand? If we say 8 persons, then automatically means what we need in that house is 800 times 8. However, in water reticulation design, there's what we call safety factor. You must include safety factor. And that safety factor is between 1.3. When I say safety factor 1.3, you know that I'm increasing the value by 30%. So 2.3 based on German standard. This is the safety factor we use in water reticulation design, between 1.3 and 2.3. The value to use now determines on the number of capita or the population equivalent. As the population equivalent is getting bigger, the safety factor becomes smaller. But if the safety factor is smaller, use a bigger safety factor. Let me repeat it again. If I'm designing for 10,000 people, I might use a safety factor of 2.0. In other words, I'm doubling the demand. It's normal. That's the law. That's the rule. But if I'm doing a design for 4 million people, my safety factor can come down to 1.5 or even 1.3. In fact, anything above 1 million, your safety factor comes to the minimum. In other words, if I'm designing for 100,000 population equivalent, I only need to provide extra precaution for 30% extra. But if I'm designing for, say, 5,000 people, I will design precaution for 100% extra. In other words, I might expect that tomorrow, this 5,000 might become 10,000. But it's more difficult to assume that 1 million will become 2 million. It can be like Abuja. Abuja, they use 100 liters per capita per day, but used a safety factor of 2.3. But they knew that it's going to be an explosive city within a short time. And it happened. Within the 30 years of Abuja, Abuja have exploded. All of us know. That's by the way. So now, back to the 3-bedroom. Now that I have 100 liters for one person, multiply by 8 persons, I will now multiply by safety factor. Let me choose 2. That becomes 100 times 8 times 2. It means
sir.
I need 1,600. Yeah, go ahead.
Yes, we assume for 10 persons. You're
Oh, 10,
using
sorry.
8 here.
Sorry. Well, 10 is on the high side, but let's just assume it. Yeah, so this becomes 2,000. Gentlemen, I think, and ladies, I think it's making sense. That's why if you go around your houses in Abuja or wherever you live, the average 3-4 bedroom house, you only see it with 2 liters, 2,000 liters GP tank. So that's
Correct.
what it means. That's averagely. Sometimes we don't consume it because sometimes we're not up to 10 in the house. But this is what water. Now let me say this, and it's a universal statement. It is better to oversize an infrastructure design. I want you to sink in. It's better you over-design than you under-design. In water reticulation design, you are expected to over-design by 200%. It's like a rule. It's like a rule of thumb. When we enter module 2, it's better if the drainage size you need is 600 mm, but you provided 800 mm. You are a better person. You're a better designer. The only difference or the only challenge is that your cost will be higher than your competitors. And that is why when we come to that module, if you are designing for storm, you must ask yourself, is it a 10-year return period rain? Is it a 20-year rain? Is it a 25-year rain? Because the designer or the consultant who does the design with a 50-year rain and the one who does with 10-year rain, this one might get 2 billion, this one will get 4 billion. Then suddenly the governor will say your design is expensive, without knowing that you have used a safety factor of a 50-year rain or a 50-year storm. Whereas the other man have just designed for a 5-year storm, that after some few years and flood comes, it will destroy everything that man is happening in Abuja, in Lokogoma, in some areas. The private developers are designing rubbish. They are designing what I don't know. You see them designing small drain. The only city I have gone to, and I commend the person that did that design, is Oka. I went to Oka. I saw their drainage design. Another one that is happening now is Asaba. I know this consultant that is in charge of that work. He has come for this training in 2018. He's working, he's supervising CCECC and one other Lebanese company. If you see the drain he's doing in Asaba, they are like 3 meter by 3 meter. I'm telling you the truth. Those of you who know Asaba, Asaba is a lowland area at the bank of River Niger. Every single flood will flood. I'm digressing, but it's all for good. Every single flooding will flood Asaba. So in infrastructure design, it is better you over-design. Because there can be population. If you under-design, it will still work. The difference is that instead of providing a 3-inch pipe, a 3 inches pipe, you are providing a 5 inches pipe. Yeah, it will cost extra money and they'll laugh at, but it will still work. But if you are supposed to provide a 5-inch pipe and you provided 3 inches pipe, there's a problem. How many of us we forget those days in our university? That if you go to fetch water around 7 a.m. or 6 a.m., the water in the tap will not be running, or it will be running like small baby urine. I don't know what to use. But late in the midnight, when nobody is fetching water in the hostels, there will be water. The water will just be running normal. I want you to picture 20 years ago, 15 years ago, 25, 30 years ago for some of us. That is a consequence of poor design. But I don't blame them. You know why? Because our people are erratic in development. Nobody uses university master plan. If you use university master plan and the university says in 50 years, we're going to have 10 hostels. But now we are building only 2 hostels. A good designer will provide pipe for 10 hostels. All you need to do is to plug it. You go to the end. Let's say it's hostel A, hostel B on a straight line. Once you know they are hostel A, hostel B, you plug. That's what they did in Owerri with the design. When the white men, when Owerri was the capital of the oil industry in Nigeria before the war. If you go, you see that they expected, they knew that police people is explode. So what they did was they are using plug. So they use let's say a pipe diameter of 1 meter. So as it's going down, as the city is developing, is from 1 meter it will get to 800, from 800 it will get to 600, from 600 it will get to 400. As the city is developing, the pipe is decreasing. But for a start, they started with 1 meter. But a poor designer will design for 2 hostels. And then when you now build the 3rd hostel, there's no water in that hostel. Because the pipe sizing is poor. Because if you use 3 inches pipe as against 5 inches pipe, it will only take for 2 hostels. But the 5 inches pipe might have taken extra 3 hostels. I'm just giving you an idea for you to see why sometimes Mr. A has water, Mr. B does not have water. It's a consequence of poor design. And that is why this training is important. At least to expose you to those things so that when your staff is doing design water, when they bring your water design, if you look at it, you just calculate and say, okay, what is the population of this place? Okay, we're going to learn all these things when we start the design. And then you begin to say, okay, will this thing work or will it want it to work? You know. And as the pipe is going downstream, you begin to see if there's a gradation. If it's just the same pipe, unless it's the same main pipe, then it taps off into the streets. It taps. Good and fine. But if there's going to be future development at the down end, then you need to know that the pipe size needs to be consistent so as to coordinate to accommodate the down end. So here again, this is what we need. But if I now want to pipe the size that will deliver this quantity of water, then I need to reduce it to liters per second. So I need to change it to liters per second. That is what we use in our design. So to change it, it means I'll divide this 2,000. Here, we said 1 day is 3,600 seconds. So I'll divide this by 8,600. That will give me 0.02 liters per second. Please, any question? Is he understood? Any question here? Did you all understand this? I hope so.
Yes, sir, it's understandable.
Okay,
Yes,
good. Now, the idea is that you need the lowest. It is this value that you now use to determine your pipe size. Because you need this water to flow to this tank through this pipe. So what size of pipe can deliver 0.023 liters per second? You no longer use this 2,000. This 2,000, you use it to design your tank. You design your tank based on daily demand per day. So I need 2,000 liters per day. Good. But when you come to pipe is a smaller discrete parameter. So what you do, you scale down and also discretize that to the barest minimum value, minimum unit, sorry. And that minimum unit is liters per second. Liters per second. So, since there's no question, we'll continue. So, I hope this is understood. So, after now, let me finish up. After now, you now go to your pipe sizing. You go to your chart. Like I said, before you now use Manning N. You now use that Manning N. Let me look for it. But we are no longer in the days of formula. If you go to online, you say Manning's equation. Or Manning formula. It will bring you that difficult formula to calculate your Q. Okay? Or from your Q, you now calculate your pipe size. How many of us have forgotten this formula? Q equals to AV. A very well taught universal formula.
Don't forget this one.
Q.
We can't say the formula here, right?
You cannot forget that formula.
Have you seen it?
Oh, write it completely, please. Write it completely, please.
Q is AV. Remember, this is called the law of continuity.
Exactly.
Discharge, where Q
Continuity
or big
equation.
Q is the flow or discharge. A is the surface area. Remember, hydraulics, engine 309. Some of you that 30 years ago. Surface area. And V is the velocity. Velocity or, listen to this, or discharge. Discharge per seconds. I don't know how to put that one. Now, this formula can also be written as, which other way can I write it? Q, EQ equal to small q times small a, whichever way. Where Q, small q, is in liter per seconds. Who remembers that? And A is in what?
Area.
Area. And then BQ. The answer to BQ will be meter cube per seconds. Of course, gentlemen, is that not what it is? Remember, here it's just a question of 1,000. Or meters per seconds. If it's huge, big enough, this and this are the same. It is just 1,000 here. I believe we all remember.
Sure.
So this is what it is. So why I'm bringing this to us is that if I get my discharge, I just need to have the discharge, and I'll get my focus here is to get the A. If I get my A, all of us know that A is pi. I don't know how to write pi here. Pi formula here. 3.142 times radius square divided by 4. Depends on where you school, but something like that. Arrow square can also be arrow square. Arrow square But if you're not using diameter, oh, this is this.
No, it's this square, not R.
Not
Thank
R.
you, sir. This
This
square.
square.
Same thing. This square over 4. So, but all this thing now is what you can do from charts. Because I just went through online now and I saw the huge Manning's N. This is Manning's formula to get your Q. So you need to consider the R. R is the Manning's R. A is the surface area. S is the slope. So all these formulas, this is for Manning. If I go to say, if I come here now and say Chasey Manning, Chasey Manning, you see a modified formula of the Manning. Okay, look at it. Then if I say Dashi, Weisbach, Weisbach, that's the Weisbach formula. Look at his own. Look at it. This is Weisbach. Look at it. To get the pressure, all these things, we were going to do them anyway. But I'm just telling you that there are other many intricacies that the best option is to use a chart. Some of us who are civil engineers, remember those days, column design, slab design. We don't use formula, we don't calculate fire formula. Rather, there's a chart behind our textbook for some of us who did this as open book, which is the right thing to do. Remember those days, just put your mind. The point I'm trying to make is that in our world of today, engineers, we make use of chart a lot, especially when it comes to pipe sizing. You don't need to start calculating formulas, cramming formula, like this formula for head loss. Head loss, frictional factor from velocity square over 2g times the diameter. Nobody's doing all this thing again. Absolutely. So what we are doing now is to make use of charts. And that brings us to our charts. That if you get this formula, the next thing you need to do is to go to your chart. I'm done with this. There's still a lot to learn here, but I'm of the opinion that some of us can learn it on our own. Okay, I've muted those who didn't mute themselves. Okay, so let me go back here and finish up here and make sure that I finish up this. So once you've gotten the this value, you now go to your charts. Let me bring a copy of the chart. The charts are called monogram. Those are those charts with you. We call monogram. I'm going to use the one. You can see my screen. So look at my screen. So in your material, there is what I call monogram. You can download anyone online. In fact, last time I downloaded one from US Highway. So this is monogram. Monogram 0.1, monogram 0.4, and monogram 1.0. 1.0 is for concrete pipe. You don't need it again. 0.4 is for ductile iron. That value is the frictional factor. The one we are using now, which you know, is PVC or MPVC. That's the one we are using, monogram 0.1, because the frictional factor is very low. The frictional factor is very low. That's what we're using. The frictional factor is very low. Very low. So open the charts. Let me show you how to use the chart so that you can practice within the week. This chart was actually developed by my university, my former university, University of Stuttgart. But like I said, go online, there are many charts. Any chart you download, you just study how to use it. That's just the thing. This chart has horizontal and vertical. The horizontal is showing you the flow, the discharge, the Q, the big Q. Everybody can determine the big Q. So if we are 10 in a room, I simply multiply my demand times 10 times safety factor. That's just the way to get the total demand. So if my single demand is 100 liters, and I'm designing for 10,000 people, I'll just say 100 times 10,000.
I hear you very well. It's not audible.
Okay. Okay. You hear me now? From this, if I'm asked to design for Wuse zone 2, and I was told that the population of Wuse zone 2 is 20,000 people. Call it population equivalent, PE. All I need to do now is to say the single demand is 100 times 20,000. And then safety factor. Let's say I choose 2 again. Yeah? And the value will be what? The value will be 20,000 times 2 times 100. The value will be 4 million liters.
4 million.
4 million liters per day. Per day, liters per day. Remember, this 4 million liters per day is the same thing as 4,000 meter cube per day. Remember, right? If I now want to now use it to design a pipe, I will now say 4 million divides 8,600. It will give me 46.3 liters per second. So it means in Wuse zone 2, I need a pipe that can deliver 46.3 liters of water every seconds. Every seconds. And if I'm to design a tank for them, I need a tank that can store 4,000 meter cube of water. But if it's for single day storage, if it is for half day storage, I'll divide it by 2. The reason is that most times you don't store water for the whole day. You recharge every 12 hours. You pump back the water every 12 hours. In fact, let me tell us the story. Lower Usman Dam, they pump water every 30 minutes because the tanks they provided in Abuja have been oversubscribed. So if you keep water in the tank, okay, let's say those 3 bedroom we did. Let's assume that there are now 4 units of 3 bedroom, and you pump 2,000 liters of water. You can't do them now. It means you'll be pumping water 2 or 3 times every day. But if instead of 10 people, you're now 5 in the house, automatically you'll be using that water for 2 days. But if people are now 20, you'll be using that water for half day. So that is the proportion. Understood?
Sorry, so. Please, can you come up again with this ask for Wuse? I couldn't get. What is the 100?
The 100 is the total demand per person.
Okay.
The 100 is total demand per person. The universal value.
Okay.
Is based on standard, yes. Yes.
Okay.
Then the population of the Wuse is 20,000 people. And the 2 is the safety factor required of you that your water reticulation infrastructure must be designed to accommodate 200%. Is a German standard, it's also a European standard, is a British standard. Let me tell you from my experience why it is so. If you lay a pipe inside the ground and you get it wrong, that pipe is gone. Can't bring it out. If it's a PVC pipe. So now, let's move again. So I want everyone to go to that chart. Go to the chart with 0.1. Go to that chart again. So if you go to this chart now, we're using 0.1. We're using 0.1 because we're using PVC pipe. We're assuming we're using PVC pipe. We are assuming, the assumption is that we are using PVC pipe. So PVC pipe has a very low frictional factor. If you touch the body, you see that it's very smooth. Unlike concrete pipe that has 1.0. These days, we usually use concrete pipe for, well, we don't use it for drinking water again. Ductile iron is 0.4. It's still very good. Depending on the kind of lining, these days you see ductile iron, but it will be lined very well. So the frictional factor will still be low. And which is a good thing. The lower the frictional factor, the ease of allowing water to flow, and the less the losses. Understood? The smoother the pipe, the less the loss. All of us know what friction means. Okay. On the horizontal is the slope. You use, in this chart, you need to input parameters. Remember those 4 parameters I told you about? You give him 4 parameters, you give him in 2 parameters, it will give you out the other 2 parameters, then you go to your detailing. On the diagonal is the pipe sizes. Look at this. This is 101 mm, this is 900, this is 800, this is 600, and so on and so forth.
Please show your
screen. We are not seeing the chart. We are not seeing the chart.
Oh, sorry. But download it in your material.
Yeah, we know, but we have to listen to you now.
Some of us don't even have this
Download it.
material.
Everybody study the pipe. Bring your pipe. Bring out the chart, sorry. Horizontal and vertical. Just try to have an overview of it in 2 minutes. Just in 2 minutes. Let me take 2 minutes and study this pipe, because this is the game changer. And not only here, in every civil engineering design, there's use of pipes, use of charts, sorry. So on the vertical,
so which one is the
sorry?
Which one is the chart? Is it the
monogram? The monogram. Nomogram. You see nomogram. Go for the one. There are 3 of them I gave you in the folder. Go for the one for 0.1. On the horizontal is your discharge, is water demand. Like we calculated for Wuse. Wuse requires 46.3 liters per second for a population equivalent of 20,000 persons. So we want to calculate what is the main primary pipe we should just pipe to Wuse from the tank along Kubwa Road, supplying Wuse. What size of main pipe should we first of all take? That main pipe is important because it is the one that will now tributalize as it goes down to form tributaries of lower pipes. If you get it wrong.
So I want to get how we now use the pipe because we can
the chart.
Yeah, the chart. We can see
so if you go to the chart now,
the slope
is in per thousand. The slope is per thousand. So we need to now determine, if you now go in real life, you now ask yourself where the tank where it is located and where the people are living in Wuse, or the lowest point in Wuse. No, see the lowest point now? Yes. No, the highest point in Wuse. You use the highest point. The reason is that if the highest point can get enough water, the lowest point does not have problem. In fact, you will get more water under higher pressure, which is, remember, we want water with the required pressure. If the pressure is not there, the water will not flow. Some of us will put our bucket in our bedroom on the tap. You can go to work and come back. The bucket is still there. That's a function of poor design. There should be a certain pressure, a standard pressure in a pipe network, in a water pipe network. Adequacy. Not too high, not too low. we say it's about 2. Okay. Now, this slope, and that is the only thing you need to understand about this chart. The slope is calibrated in per thousand, not the percent. Percent means per 100. Per thousand means per kilometer or per thousand. So this chart is calibrated based on per thousand. So if you say slope of 0.5, what we're talking about is 0.5 per thousand. I want this to sink.
1,000 meters.
1,000 meters or 1 kilometer. Thank you. So if I say a slope of 1%, 1 or 1%, you know, okay, this goes back to mathematics. If I say 1%, it means if it is 100, that 100 is 1 meter. But if I say 1 per 1,000, it means 1 meter per 1,000 meters. Okay, the cocoa is that if the value you get is 1%, then the value you use here to get the same thing is 10%, 10 per 1,000. 10 per 1,000 is something as 1 per 100. Are we together? 1 over 100 is equal to 10 over 100.
No,
10 over 1,000. Mathematics. 1 over 100 is something as 1 over 1,000. Is it as 10 over 1,000? Sorry. 1 divide 100.
Correct.
Equal to 10 over 1,000. Percentage is talking about 100 per mil. Per mil, if you go to the hospital, they measure your blood sample or do something. You see them saying 2 per mil, 3 per mil. What they are saying
correct.
Is that, what they are trying to say is that we took 1 mil, which is 1,000 of a liter of your blood sample, and we saw 3 parts of that bacteria inside, or whatever they are looking for. So, you know, all of us are used to percentage, but there's another per mil. Per mil means that the unit of measurement
Sir, we can't hear you clearly.
is from your own end, please. Your network is bad, sir.
Is your network? Your network is.
Check your network. We're hearing him.
Okay, so that is what it is. So let's go back to Wuse now. Are you okay? Now go back to the chart. So
okay, you can continue, no problem.
Okay. Let us assume that we're dealing with 0.5%. It's even high, but let's assume. What did I say? 0.5% slope. So it means in this chart, we're using 5 per mil, right? Multiply by 10 becomes 5 per mil. So you come here.
Please open your chart now.
Yes, I'm opening it. Let's see my chart.
Thank you.
Okay. So you come on the horizontal. When you come to the horizontal, you look for 46. Somewhere here, look at it. Are you seeing my cursor? Between 40 and 50.
No.
It's 46.
Okay, yeah. Yes,
you
yes.
Go up, you go up, you go up, you go up. You go to where you have 5. Look at where I have 5. Then you go up, you go up, you go up, you go up. You come to where 2 of them are meeting.
What does 45 or between 40 and 50, what does this signify?
Is the liters discharge flow or water demand for Wuse per seconds based on the population equivalent of
46.3.
The flow rate.
Yeah, 46.3.
Okay.
In fact,
okay.
if you want, in fact, make it 50. Give another safety factor to it. Make it, let's assume 50, approximately 50. The more the better. So we go to 50 and go up, go up, go up, and look for where 5 is. You see that it's falling between 200 and 250. Somebody confirm. The pipe size is between 200 and 250.
The 5 is for what?
It?
What is the 5 for? The 5, what is the 5 for?
5 is the slope.
Yes,
we say that the slope, elevation difference.
Okay, okay.
Okay, this slope, how do we determine it? Is it chosen arbitrarily?
Yes, exactly. Is it assumed?
From survey.
Hello.
Yeah.
From survey, point to point. Usually spot height.
How do we determine the slope?
We have lost him, but you are saying that, like, for
I'm here. The slope is a different thing now, but we can digress that thing from next week when we start the manual design. You remember today's introduction. The slope is the difference in height.
Okay.
Listen, the slope is the difference in height between the highest point and the lowest point. All of us know what slope is.
Yes, divided by the distance.
Divided by the distance, thank you. That will give you the slope. If you are at an elevation of 342 and I'm at an elevation of 341, and the distance between me and you is 100 meters, then it means our slope is 342 minus 341 over 100, which means 1 over 100. So the slope is automatically 0.01.
Yeah, I know people will have that challenge. That's why I threw the question.
Yes.
Please, before we leave the chat, I have a question. Sorry, sir. Before we leave the chat, can you hear me?
I'm hearing you, sir.
Please, sir, let's now trace the velocity of flow. If I check it, after checking the pipe side, I now trace the velocity of flow. I'm having about 2.5 to 2.7 meter per second. Is that a good one for that run?
No, but we're just making an assumption. We don't know. This is like in real life. Say what you said again.
Now, if you check our 5.0 now, when we trace it to that flow rate, we selected a pipe of about 200 to 250 mm diameter. Now, if you further trace the velocity of flow, you know your velocity of flow is at the, I don't know, is at this side.
Yeah, go ahead.
Yeah, if you trace it, you're having about 2 to 2.5 meters per second.
No. What you're having is 1.2 to 1.0. The velocity is falling between two velocity lines. One is 1.2, the upper one is 1.2, and the down one is 1.0.
Please, can you help us show your cursor to it so that it's clear?
Look at it.
Straight. Okay.
He's here.
Yes.
And here is falling between two lines. The upper line is 1.2 velocity. The lower line is 1.0 velocity.
Okay, fine.
And the minimum velocity in a pipe network is 0.3. The maximum velocity is 3. If your velocity in your pipe network is more than 3, it will lead to bubble formation, or we call it will lead to negative pressure. It will lead to supercritical flow. Then if it is less than 0.3, it might lead to aging, water aging. The water will not be flowing, as in over time, algae and some microorganisms will form because the water is not flowing. Remember, microorganisms, they don't stay where the water is flowing. Remember, that's why some areas in some parks in Abuja, in the past, they used to smell, but now they've learned it. So they need to make sure that those water are flowing. Anyway, you see flowing water, you can't see what's inside. You can't see what's inside. As long as water is flowing, you can't see formation of algae, spirogyra, and other aquatic organisms because the speed is minimum, is optimal, sorry. So the velocity here is between 1.2 and 1.0, and that is so perfect. Why the pipe size is between 200 and 250.
That's sorry, where do we identify that velocity in the graph? I'm trying to look at it.
Is this parameter, you put in 2 parameters, you get 2 parameters. If you follow this line now the value is somewhere here. So, yes. So 2 lines are bounding the value you got. One on the up, one on the down.
Yes.
So follow that line straight. This is like a psychometric chart. How many people are doing psychometric chart?
The upper line
is 1.2.
Okay.
The lower one
and
is 1.0.
And 1.0. All right. So and diameter 250. Okay, within the region.
Yeah,
okay.
We are using 250 because it is between 200 and 250. So you use your wisdom and choose 250 because it's better to over design.
The upper limit, yes.
And those pipes are also written based on what's available in the market.
Yes, market sizes,
yes.
availability.
Market size. So you don't get 225, 7-inch pipe. If you go to market, you might not see.
That's the standard.
Standard, yes.
Yes. You can even choose 300 diameter.
No, sir. You can't.
Okay, it's higher.
You will be a wasteful consultant. How can 250 is adequate? Remember, the value is even 40 something, but we will increase it to 50.
Okay.
So assuming that value is even 40.
What of availability in the market?
No, 250 is available.
Okay, so it's all right. Go ahead.
250 is 8 inches. It's 10 inches.
Go ahead.
If you choose 300, it's more expensive. Your design will be more costlier.
That's 1 foot, which is much.
In fact, if this value is 40, the thing will be 200.
Yes.
Yes,
because it was 46.
That would be 1 foot. Yeah. Question. Before we continue.
It's clear, sir.
Sir, can we get the video of this lecture after the lecture is set?
That's an agreement.
Sorry, once again, the unit of the slope we have.
1,000.
Per 1,000. Okay, all right.
That's why you see 0/00.
Okay. What is the 00?
What was the question that the lecturer said is an agreement?
The video is available. Will be available. As soon as Zoom process it, I'll send it to the group. Video of this class.
Sir, can I ask? Can we get the video of this lecture after the lecture itself?
Okay. Let me quickly pause the video now. Stop the video.
Sir.
So that
let's finish the lecture. In some of these things I've done, I think the way this thing is done is that all the videos are being articulated together, then and forward to us. At times we need to study in advance. It depends on the organizer how he wants it.
Yes, let's continue because if you pause it now, we may not be able to get.
Let's get the lecture first.
Okay, we are running up in 5 minutes. Okay, well, we are done. We are done. This is like a question and answer time, but let me round up in 5 minutes. So now we have determined that we say requires 250 diameter of pipe. That is the main. But now this is the point. That pipe size is just the main. As it enters, we say you want to go into Ademola Tokumbo, you can reduce it to 150 based on the population of people on Ademola Tokumbo. As it's entering to smaller streets, it will turn to 100. But the main is like the head. If the head is wrong, all the other part of the body is wrong. That is why, if you see in my presentation, I mentioned something to that effect. I mentioned about the different area because I've seen design where people only design the main. They design the main and leave the design. Why? And I know why. The reason is that if you're able to design the main, the tertiary and the other ones are no problem. Like every plumber in this world knows that you need the 1 inch. Pipe. If you're the only one living in your house, 1 inch. But if it's a big company, the pipe in your kitchen is 1/2 inch. The pipe in here, so that one is not even in this training. But for the infrastructure design, which is why we are here, the infrastructure design, which is why we are here, you have to consider that. Any question? So look at this chart. So here now, gentlemen, you can see that the demand this place is 240 liters per day. So what I wanted us to do and what is the assignment for this week is that get me the pipe sizes for each of these areas. So in other words, Industrial knot. What is the pipe size? But listen to this. This is German way. German's point means comma. Comma means point in German. So this industrial knot is 2,942.8. 2,942.8. That is what the industrial area needs per day. Add this thing to liters per second and get me the pipe size. So how many are they? There are 1, 2, 3,
1, 2, 3, 4, 5, 6, 7, 8,
9. Now let me give you a trick. Let me give you a trick. Anybody who gets commercial east and gets commercial south, you can use the volume for commercial south for commercial east. Why? This one is 709.5. This one is 706.5. Gentlemen, after a while, you discover that you don't need to be computing for everything. Once the population equivalent of any area within Abuja now is 20,000, what value will I use? 250 diameter pipe. I don't need to go back and start doing any calculation. No, because I've done it before. In fact, if I see a place where the population equivalent is between 18,000 and 20,000, I will assume worst case scenario of 20,000. Those of you that are structural engineers, you know what we do in beam. Once you do a beam of 4 meters and you see a beam of 5 meters, you can use the volume for 5 meters for 4 meters. True or false?
True.
Yeah, quite
if you
true.
have a slab of 5 meter by 4 meter, and you see a slab of 4 meter by 4 meter, you'll be wasting your time going to redesign that slab. Just use the parameter for 5 meter by 4 meter. Only that you are being lazy, right? You are being wasteful.
That's most critical.
That's the reference.
Exactly.
That's the worst case scenario. If I do a design for an 8 meter beam, I can use the same design to do 6 meter, 5 meter. But when it gets to 10 meter, I will redo it. So if you do for this one, you can use it for this one. If you do for this one and you are lazy enough, you can use it for this 198 and 240. Whatever pipe size you hear, you can easily use it here. So this is the assignment for this week. So design this. Why I'm saying this is some people just design the mains. I've seen a design from Federal Ministry of Water Resources for Ofoma, somewhere in Umuahia. And I discovered that they just designed the main. And I don't blame them. Because once you design the main, people will just come and tap up and the thing will work. But when the main is wrong, everything is wrong. So this is 12:20. We added 20 minutes extra because of we started also 20 minutes late. So we'll make up. Every other day we don't exceed 12 o'clock so that you can go and do other things that you need to do.